speaking about Maximin D-optimal designs for binary longitudinal responses.
Okay, thank you. Also, I want to thank the organizing committee for giving me this opportunity to present part of my work. It's part of my research project with Frans Tan and Martin Berger in Maastricht University in Holland. So as you can see, the title is Maximin D-optimal designs for binary longitudinal responses. So I'm going to repeat some of the issues mentioned by previous speakers briefly, and then I will describe the D-optimality and relative efficiency we have used in our study, and present Maximin D-optimal designs, which is the major part of our work, and give a numerical study and results, and conclude my talk by giving some concluding remarks based on the results of our numerical study. So as you have seen the title, it's about longitudinal binary responses, and we want to have a design for binary responses which are taken repeatedly over time. So we are going to use a model which is appropriate for such responses, and this model is nonlinear model, and this nonlinear model the design depends on unknown parameter values which are not available at the design stage. So that's the problem technically, and some of the solutions suggested in literature are just to start with initial values and get designs which are optimal around these initial values, and also to have sequential procedures. Start with initial values and do your experiment and update the parameter values and continue with the experiment. And the other solution is to work with Bayesian approach by assuming certain prior distribution for the parameters. And the fourth approach is Maximin approach, and this approach we try to find a design that maximizes the minimum efficiency, the minimum relative efficiency in a user-defined parameter values. So in our case, we will focus on this last approach in the context of longitudinal measurements with binary responses. So the objective is to find designs which are appropriate for binary longitudinal responses. We can have different models to analyze such data. One of these models could be mixed effects logistic model, which we have considered in our work. So basically we want to investigate locally D-optimal designs at specific values of the parameter, and also we want to identify Maximin D-optimal designs which combines the Maximin approach and with the D-optimality criteria, and we also want to know the optimum number of time points to take the measurements. So from practical point of view, we have two questions. One is what is the optimum number of repeated measurements, and the other is where to take these repeated measurements over time. First, I will briefly introduce the model. The model is just the mixed effect logistic model. If we have q repeated measurements, q binary responses, and each one of them will have Bernoulli distribution with probability, conditional probability of the response is success, given that the random effects bi's, where these bi's, the random effects, are assumed to be multivariate normal with zero mean and the variance covariance matrix G, and this probability is related to the linear predictors through the logit link function, and the linear predictor has two components. The first part is the fixed part, and the second part is the random part. In the fixed part, we have the design vector x prime sub j, and beta is the fixed effects parameters. Usually we are interested in estimating this parameter, so the question is, what are the optimal design pointers to estimate this fixed effects parameter optimally or in efficient way. And the second part of the linear predictor is the combination of the coefficients of the random effects, and this vector could be a sub vector of the fixed part, and the fixed part could contain different covariates, values of different covariates, but in our case we have assumed only the time points, so we don't have extra covariates. But in general, it's possible to have more covariates within this design matrix. The estimation for the previous model which we have given here is a little bit difficult, because the likelihood function is usually involves the product of the Bernoulli distribution and the multivariate normal distribution for the random effect parts. So it's difficult to get the closed form of this likelihood function and get the solutions. So in literature, different approximation methods have been suggested. One of the numerical approximation methods which is popular is the PQL method, the penalized quasi-likelihood method, such as discussed by Breslow and Clayton in their 1993 paper. And in their work, they used Laplace approximation to approximate the integral of the log likelihood function and obtain PQL. And we are more interested on the variance of the variance covariance matrix of the parameter estimators for optimal design purpose. So here I gave the expression for the variance covariance matrix of the parameter estimators. The variance covariance matrix of the parameter estimator is approximated at the end of the iteration procedure by this function, where x is formed by stacking the design vectors which are here, and v at the center is the block diagonal matrix which blocks q by q matrices given by this equation, where wi's are the diagonal matrix of the conditional variance of the responses given the random effects. We have also considered extended GE method. David was talking about GE method, and here there is extended version of GE method which considers serial correlations and random effects side by side in the model. And Zeger and colleagues have discussed about this extension for GE method, and at the variance covariance matrix in this method is approximated by using this equation. The difference is here with this the expressions in the middle. The working variance covariance of the response VI is given by this equation. Here the correlation structure is introduced, so we have the serial correlations and random effects side by side. Here in our work we have considered the AR1 correlation structure, which is the autoregressive with order 1. So now we have the approximate variance covariance matrix in both methods. The next step is to consider the D-optimality criteria, and in the D-optimality criteria, as most of you probably know it, it tries to find a design that minimizes the determinant of the variance covariance matrices. So a design is D-optimal if it minimizes the generalized variance or the determinant of the variance covariance matrix. Here we have the design space. The design space consists of all designs with Q repeated measurements where each time point is an element of certain interval of time points or the steady period between A and B. The steady period A could be the starting point of the research and B is the end point of the research. So in short, A and B are just the two endpoints of the time interval. To compare two designs, we can use the relative efficiency. The relative efficiency is just comparing the determinant of the variance covariance matrices for two different designs. In this formula, we wanted to compare the design with Q repeated measurements and a design with number of repeated measurements is equals to P, where P is the number of parameters in the model. So here the determinants are adjusted for the differences in the number of repeated measurements, because this design has Q repeated measurements which could be greater than P, and this design has number of repeated measurements exactly equals to the number of parameters in the model. Yeah. Then introducing Maximin D-optimal designs, it has been already discussed in several literature, and Maximin design is a design that maximizes the minimum relative efficiency over certain space of the parameters. The parameters are the parameter values, I mean. So if you have a certain space or interval for the parameter values, so we are trying to find a design that maximizes the smallest relative efficiency over this space of parameter values. And the corresponding efficiency for the Maximin design is Maximin efficiency given by this formula. And we considered numerical study because we couldn't find analytical solutions for the designs that we wanted to identify. So we have considered time interval between -1 and 1 without loss of generality, because D-optimality has an interesting property that you can transform the time interval to another scale and still you can have the same optimal designs by using the same transformation for the results. In this case, we considered time interval between -1 and 1, but if somebody is interested to get the optimal designs, let's say between first year and 5 year, then by using the same transformation, the results can be transformed. And we also considered random intercept and slope models with polynomials of time, linear, quadratic, and cubic terms. And for the Maximin D-optimal designs, we have considered two different intervals of parameter values, because we have to define certain interval for the parameter values, and we want to see the sensitivity of the Maximin D-optimal designs for different intervals of the parameter values. We have considered the first interval with reasonably small, or the values which are common in practice, and another interval with large interval. When you convert these values of the parameter betas into odds ratios, this odds ratio could be large, which may not be common in practice, but we have considered these two different intervals just to see how the Maximin D-optimal designs are robust for different values of the parameter values. And we wrote a MATLAB code which mainly used fmin con function of MATLAB for the optimization of the determinant of the valence covariance matrix and to obtain the locally optimal designs. This is some of our results. Here in these plots we have a number of time points varying from q is equals to 2 to q is equals to 5 in this particular case. And the first column, this column shows the result for PQL method, and the last two columns shows the result for the extended GE method. This means the mixed effects logistic model with serial correlations with a R1 structure. And the results show that, first the horizontal axis, this horizontal axis shows the design pointers starting from -1 to 1, because that's the interval for our time pointers, and the vertical axis shows the parameter values. In this case, for linear model, the parameter values from 0 to 3 for the slope parameter, and we fixed the intercept parameter to certain value. In this case, we fixed it to 1 for the intercept, and the same for other plots. But the difference is that in PQL method, here we have optimal design pointers when q is equals to 2 for linear model, at -1 and 1 for small values of the parameter values. And when q increases, when we add additional measurement, then those additional measurements, they are close to one of the design pointers what we had for q is equals to 2. But in the case of the extended GE method, the additional design pointers, they are far from the two end pointers, and they tend to come to the center, or when you increase the number of repeated measurements, they tend to behave like equidistance time pointers. And the other interesting feature is that when the values of the parameter values increase, the design tend to move away from the end points. When we have the parameter values, let's say less than 1 or 1.5, the two end points are included in the optimal design points. But when the values of the parameter increase, the design does not necessarily include the two end points. This is what I have already said. And the result for Maximin D-optimal design, here we have the model, the random intercept model with linear, quadratic, and cubic terms of time, and the number of repeated measurements, and the PQL method, the result for the PQL method. Here we have the Maximin design at -1 and 0.56 for 2 repeated measurements in the case of linear model, and the corresponding Maximin efficiency is 0.78 when the parameter values are in 0 and 3. And these are the corresponding values for the extended GE method. And the second part of the table shows the results when the values of the parameter, the interval for the values of the parameter are between 0 and 1.5. Here we can see that the Maximin efficiency is higher when the interval of the parameter values is narrow. And the other interesting feature is that when we have this interval of parameters, the Maximin efficiencies are reasonably high. we have also computed the relative efficiencies for Maximin designs. Here in the case of linear model, for example, in the PQL method, as the number of repeated measurements increase, we try to compute the relative efficiency of the Maximin design, for example, with 3 repeated measurements relative to the Maximin design with 2 repeated measurements. As we can see from this curve, it's decreasing. This means the Maximin design with 2 repeated measurements is more efficient than the Maximin design with 3, 4, or 5 repeated measurements. The same trend can be observed in all other cases. For example, in the case of cubic, when we have 4 parameters in the model, and in the extended GE method with the correlation coefficient 0.9, it's decreasing. The relative efficiency is decreasing. That means the relative efficiency of a design with 5 repeated measurements is less than 1. That means a design with 4 repeated measurements in this particular case is more efficient. As we can see here, these Maximin designs and also some of the locally optimal designs, they do not include the endpoints of the time interval. But in practice, researchers they fix the starting point and the end point of the study. So we also try to compute the relative efficiency of designs which include the 2 endpoints of the time interval. So in this case, we try to force the design to include the 2 endpoints. So they are not necessarily the optimal designs. And we found the Maximin efficiencies are still high in the case of linear and quadratic case, but in the cubic case, it's a little bit lower. And some concluding remarks. As I have already mentioned earlier, optimal design points may not include the 2 endpoints of the study period, and in most practical cases where we have a reasonable interval of parameter values, the Maximin efficiencies are still high, and a Maximin D-optimal design with number of repeated measurements is equals to the number of regression parameters in the model is the most efficient design compared to designs with more number of repeated measurements. In our work, we considered only the time points. We have not considered other covariates like treatments and control groups. So the future work could be what would be the result if you include additional experimental variables. And also in our work, we assumed that all subjects will be followed until the end of the study period, and measurements are taken in each subject. So what will be the effect of dropouts, because dropout is also common in practice. If you have dropouts, then what will be the effect of dropouts on the design? Yeah, thank you.
We have time for questions.
Do your results depend upon the variance of the random effects?
The variance of the random effects. Yeah, in our numerical study, we try to fix the variance of the random effects. Yeah, so we try to change the values of the variance of the random effects, and the results, they differ a little bit, but the difference is not really significant.
On your first point here, it's quite common in optimal designs for, or at least approximate optimal designs for generalized linear models, that the endpoints may or may not be
included. Yeah. So maybe this results in the extension of that. And now we know that in the case of not only generalized linear models, also for at least for mixed effects logistic models, this result holds. Yeah.
No other questions? Thank
Well, when you work on it, did you have some specific application in mind, or you've been working mainly for theoretical purposes?
Yeah, we had some application in mind because in epidemiological research they are collecting data on a large scale in most of the longitudinal studies. So we wanted to see, yeah, instead of just collecting data repeatedly.
But can you say something more concrete? What kind of data would that be? I mean, what application, more specifically?
Yeah, I can't. I don't remember the specific variables. You are interested on the specific response variable that we are interested in.
For example,
For example, yeah, in yeah. For example, you can collect the information on children, yeah, to see how they are attacked by diarrhea, yeah, whether a child at a specific time point is affected by diarrhea or not. So binary response, yes or no. And we want to collect this data repeatedly over time so that we can see the trend over time.
Thank the speaker once more.